A very good morning to all. Uh, Today is our class number 28, and mainly we're going to talk about radiations. So I think all of you are aware of the radiations. Radiation heat actually comes from an object which are actually radiating the electromagnetic waves. So actually, the temperature it depends. The emission of radiation it depends on various parameters, starting from temperature of the surface, the nature of the surface, and the wavelength of the frequency of the radiation, like sunlight, right, which is coming from far away. So actually that is a radiation that is depend on the temperature of the sun, which is very hot. Now emissive power, there is another terminology which you often actually encounter during radiation. This is called emissive power, which is actually related to the Stefan Boltzmann law, and its unit been given in the total amount of radiative heat, radiation emission by a body per unit area in unit time. It's given by watt per meter squares. And as you can see, the emissive power of a black body, according to Stefan Boltzmann, is proportional to the absolute temperature. That is, emissive power EB is actually proportional to sigma T to the power 4, where sigma is a constant which is known as Stefan Boltzmann constant. And it's given 5.67 times 10 to the power minus 8 watt per meter square Kelvin to the power 4. Now, one more thing is here that the temperature expressed in this Stefan Boltzmann's law for the calculation of emissive power, the temperature is in Kelvin. You make sure when you do any calculation, it convert the temperature. Let's the amount of radiation emitted per unit wavelength varies at different wavelength. So if you have a monochromatic source, monochromatic light, you actually calculate for a particular wavelength, and then it's given by the monochromatic emissive power E lambda, right? Lambda is the wavelength of that light, right? It is also defined as the rate of energy radiated per unit area of the surface per unit wavelength. And it's expressed like in this form, integration of 0 to infinity E lambda d lambda watt per meter square, because you are calculating for a particular wavelength. For emission from real surface, actually it is the same equation, emissive power equal to epsilon, because real surface actually has an emissivity. Emissivity is not one, which is actually for generally considered for black body radiations. But for real surface emissivity, actually the formula is emissivity times the sigma is the Boltzmann, Stephen Boltzmann constant times area t to the power 4. If you divide it by t area, that is then it become uh, emissive power, right? That is the equation I have already expressed. Now, emissivity is actually it's defined as the ability of a surface of a body to radiate a heat. It is defined as the ratio of emissive power of any body to emissive power of a black body, given by E by EB, right? Now, for black body, epsilon is 1, right? While for a white body, epsilon is 0. So, for a black body, emissivity is completely 1. And for gray body, it actually varies between 0 to 1. That is why the expression here, epsilon, comes here, because for real surface, it is neither white body nor black body. It's in between. So, actually, emissivity has to be considered like this, right? It also varies with temperature of the wavelengths. So let's move to the other another important parameters. I think all of you are pretty aware of during radiations. When a light actually impinges upon a surface, there are various phenomena happens. Like as you can see here, the incident radiation, which is given by G, which is irradiated on this surface. So either it's going to be reflected back to the medium, or it's going to be absorbed by the body, and some portion of the light or incident radiation is going to transmit to the body, depending on the nature of the surface, the thickness of the body, on which the incident radiation has been impinged upon. Now, the three things which are happening, actually, you can say that the total conservation of energy actually established when these three phenomena happens altogether. So if you just go by the law, then actually due to the conservation of energy, the amount of energy absorbed, amount of energy radiated, and amount of energy transmitted will be the total amount of energy, right? And if you divide it by the both side by G, then you get this relationship, which is actually given by alpha plus rho plus tau equal to 1, where alpha is known as absorptivity, that is the fraction of light which are being absorbed, and then rho is actually reflectivity, which is given fraction of light which is being reflected, and it is given by gt by g is given by tau is given by transmittivity, that is the fraction of light which is being transmitted. So I'll come to the next slide. As you can see, it's the what I just mentioned, the fraction of incident radiation absorbed given by alpha, then rho, then tau. Now, why it is so important for any body? Actually, there will be these three phenomena, But actually, from one body to another body, like say black body, opaque body, gray body, the dependent the body different reflection. What is called black reality. Black body is one which neither reflect nor transmit any part of the incident radiation, but absorb at all. A perfect black body should have alpha equal to 1, but actually in reality does not. There is no perfect black body. Even the carbon black, which is actually close to it's considered black body, is still not a black body. So actually in reality there is no black body, but we for the sake of understanding, for the sake of different calculation, we actually consider this black body radiation and consider alpha equal to 1. So, however, it is concept is very important. Let us now look into other concept, that is opaque body. When no incident radiation is transmitted through the body, it is called an opaque body. So, if the, the main incident radiation is transmitted, so no, it is either going to be absorbed or going to be reflected back. So, for a opaque body, it will be the tau will be 0, so alpha plus rho will be 1. Solids generally do not transmit unless the material is very thin section. Like metal generally absorb radiation within a fraction of micrometer, and insulator within a fraction of millimeter. Glasses and liquids are therefore generally considered as opaque. Now let us look into white body. White body, what happens for a finite white body? Reflect it all, actually light is going to be reflected back. So there will be no absorptivity or transmittivity. So actually rho is 1 and alpha and tau is 0. Now, there are two types of reflection. One is known as reflected radiation or specular radiation, and another is diffuse reflection. As you can see, during regular reflection or specular reflection, the angle between the reflected beam and the normal beam to the surface made by the incident radiation are same, right? Whereas in a diffuse reflection, the incident beam is reflected in all directions. Most of the engineering material have rough surface, and this rough surface gives diffuse reflection. If you very smooth surface, then only you can assume to have a specular reflection. But specular reflection is very difficult to get. Most of the surface actually rough in nature, and you get diffuse reflection. Now let's finally move to the gray body. In the if the radiative property alpha, rho, and tau of a body are assumed to be uniform over the entire wavelength spectrum, then the such body is called gray body. So a gray body, it will be a combination of alpha, rho, and tau. It's not going to be completely absorbed, neither is going to be completely reflect back, or nor is going to be completely transmitted back. So you get a certain fraction of light going to be absorbed, reflected back, and transmitted. So that is known as a gray body. Okay, that is actually in reality most of the body are gray body. So we have already talked about different things. Now let us briefly review this black body radiation. A black body is an object that absorbs all the radiative energy, just what I mentioned, right? Now, this is an example given for a black body. Actually, in right enter, and then actually it's reflected. Then again it's reflected. So by doing so, ultimately what happens? The entire spectrum of light which are being entered through this small orifice get absorbed. And this is so light cannot actually transmit through. This is completely opaque body, completely black body. So light cannot. And this is known actually holograms. Okay, it's actually a device which has been devised, which has been constructed to experimentally observe the black body radiations. Anyway, I think you all know what is black body radiation. I'll not go into details. You can read the slides if you need to know further. Black Stephen Boltzmann law. We're going to talk about different law. I have already discussed in the very first slide. Just to refresh your memory, as the emissive power is proportional to the sigma, is equal to the sigma T to the power 4, where T is in Kelvin, and EB is given by black body emissive power of a black body. It can be also expressed by this equation, like actually sigma is 5.67 10 to the power minus 8. So if you take 10 to the power minus 8, you can write in this form. Easy to remember, EB equal to 5.67 times T by 100 to the power 4. Let's go to the next concept, that is Kirchhoff's law. It's actually what is law states that at any temperature, the ratio of total emissive power E to the total absorptivity alpha is a constant. Okay, for all the substance in thermal with the small body is given by 1, right? Small body, which is an area of surface area of A1. Let the energy fall on the unit surface of the body at the rate EB. So actually, EB is the emissive power of the radiation which is falling on the small body Now, of this energy, a fraction alpha will be absorbed by the small body. Thus, the energy absorbed by the small body is alpha 1 m1 a1, because that is the alpha is the amount of energy which is being absorbed. So for this body, since you are using a1, that is the small body, so you can say the energy absorbed is alpha 1 a1, alpha 1 a1 eb, in which alpha 1 is the absorptivity of the body. Now, when thermal equilibrium is attained, the energy absorbed by the body 1 must be equal to the energy emitted. So what happens? What is the amount of energy absorbed? That is, we have seen alpha 1 a1 eb, right? That is the amount of energy absorbed. And what is the amount of energy radiated? That is, energy emitted is a1 e1, where e1 is the emissive power, right? Now, if you remove the body 1 and replace it by body 2, having the same absorptivity alpha 2, then it will be the radiative energy again for the absorbed by the body will be alpha 2 a2 eb, and the amount of energy emitted will be a2 a2. So actually, by considering the generality, we can write this eb actually e1 alpha 1 a1, e1 alpha 1, and e2 alpha 2. You can write it into e by alpha. But again, as per definition, we have seen emissivity is actually E by EB, right? That is the emissive power of the general body divided by the emissive power of black body. So if you write this epsilon equal to E by EB, you can express it here. So EB will be E by epsilon. EB will be epsilon. Just rewrite this equation. Now EB already have determined E by alpha. So what happens that epsilons become alpha. So epsilon become alpha. This is the Kirchhoff's law that for a black body radiation, that is at any temperature, the ratio of total emissive power to the total absorptivity is a constant, because emissive power is 1 for black body radiation, right? Emissive power 1, so actually that's why E by EB, which is actually epsilon, is become epsilon, because emissive power and alpha, that is the absorptivity, becomes 1 equal, right? Now alpha is always smaller than 1, that is for real body. Therefore, the emissive power is always smaller than emissive power of a black body at equal temperature. Kirchhoff's law states that emissivity of a body is equal to the absorptivity when the body remains in thermal equilibrium. Emissivity is equal to the absorptivity, or you can write that the same thing. You can say that emissive power is equal to the absorptivity, because emissive power is equal to emissivity for a black body radiation. And then finally, the Planck's law is Max Planck showed that by quantum calculation that the radiative intensity of a black body at a particular wavelength given by this expression, and then this parameters can be written, and you can write this E alpha lambda for a black body radiation given by C1 lambda t by minus 5 exponential into C2 by lambda t minus 1, and C1 and C2 are constant and given by this formula. Okay, these are actually useful when you do some sort of numerical, but again, this is a black body radiation at a particular wavelength, and that is why Planck's law comes into picture. This is the same Planck's law, which is, you can read this. It's very, I mean, this is very easy to understand. That actually it is being showing that as the lambda, the temperature increases, lambda actually the lambda moves towards the left side, right? It has been given, right? The peak spectral emissive power shifts toward a smaller wavelength at higher temperature. That is what is happening here. Okay. Anyway, I think you can read and then understand this. Let us consider a radiation exchange between black bodies separated by a non-absorbing medium. So we are going to consider actually we are going to derive an expression. Let us refer to figure 12.1. This is figure. We are going to actually, so what you are going to derive now, we are going to derive an expression for radiation exchange between black bodies separated by a non-absorbing medium. So light or the incident radiation is not going to be absorbed, but the radiation is happening between two black bodies. So that's what you're going to derive. So let us consider heat exchange between elementary area dA1 and dA2 of two black body radiation separated by a non-absorbing medium and having area A1 and A2 and temperature T1 and T2 respectively. So we are going to consider this black body radiation happening between two uh, elementary area dA1 and dA2, which are separated by a certain distance. The elementary area is confined within a body of A2. dA1 is in confined A1, which is having a temperature T1, and dA2 is confined within area A2, temperature T2. And the normal to the surface actually subtended angle with the center of the two radiation is actually theta 1 and theta 2 respectively, right? So each elementary, you can read this. Actually, it is very easy. Most important thing is that actually you see the rate of heat energy between dA1 and dA2 is given by d12, which is dA1 dA2 cos theta 1 cos theta 2 by r square times IB1 minus IB2. IB2 and IB1 actually is the amount of energy being transmitted, right? Is given here, right? IB1 is the black body intensity. This is the intensity of radiation for 1 and 2 respectively. Similarly, D21 is given by this expression. DA1 is given by this, and then now IB1 is EB1 by pi, IB2 EB2 by pi, and then actually finally become DQ2 this expression, right? The rate of total heat transfer of the total area A1 and N2 is given by the integration of this expression, which is coming like this. And then finally, you integrate this equation, and finally this you get this formula, right? The rate of total energy radiated by A1 is given by Q1 A1 sigma T14, and hence the fraction of energy leaving area A1 and impinging on area A2 is given by Q12 by Q1. That is Q12 is this, and then Q1 is this. So divided by this, and you actually get this formula. So most important is this. Actually, we're going to get a shape factor. The important thing is that if Q12 by Q1 and Q21 by Q2 are same, and then it is given by a formula Q12 by Q1. This integration formula given by F12, which is known as the configurational factor or surface factor, or and the view factor. Uh, Q12, F12. So you can write this Q12, Q12, this one, because this is becoming F1. So you can write down F12, A1 sigma T14. Similarly, the rate of energy by A2 that falls on A1 the other way, that from 2 to 1 is given by this Q21. The rate of total energy radiated by A2 is given by Q2 A2 sigma T to the power 4. So Q21 by Q2 this, and then Q21 by Q2 F21. Okay, and F21 is the shape factor of A2 with respect to A1, and Q21 you can write like this formula Q F21 A2 sigma T to the power 4, or from equation 12.8 and 12.10, this 12.10 and 12.8, these two formula you can see both are equal. So you can write down A1 F1 F1 times F12, that is the area of this times the view factor or the shape factor of 1 on 2, and then area of the 2 and shape factor of 2 to 1 are equal. This is known as the reciprocity theorem, and it is very useful to solve numericals. Okay, it indicates that the net radiated in that interchange may be evaluated by computing one-way configuration factor from either surface to the other. The net rate of heat transfer between two surfaces is given by either Q12 or Q21 by this formula. Okay, Q12 or Q21 both are same. Q12 and Q21 are same, and it's given by either A1 F12 sigma T14 to minus 2 to the power 4, or A2 F21 sigma T14 minus 2 to the power 4. It must be noted that this equation is applicable for black body surface only and must not be used for surface having emissivity very different from immunity. So this is the equation we have derived is only applicable for black body radiation. If it is not a black body radiation, then the emissivity will come into picture, and then equation will be different. And this is actually a shape factor given for different geometrical surface. Like this is a square which is given x and y and l, three parameters are given, and if y and by l, that is this length by this length, is varying, and then x by l is also this, then what will be the f12? So this is one, because these are actually dependent and independent parameters. So if one parameter you know, and if you vary the other parameter, what will be the shape factor? We'll see this when you do numerical. This is shape factor of a coaxial parallel plane, right? Coaxial parallel plane. So actually here it is given L by R1. L is the distance between these two plane, and R1 is the radius of this, R2 is the radius of this. So L1 by R1, L2 by R2 is given by this. Okay. Hello. Okay, let us continue. Shape factor is given for figure 12.3 for this plane separated by a distance, and finally shape factor for perpendicular rectangle with a common edge. So if this is a rectangle perpendicular to each other and having a common edge here, and if z by x is this, and then if y by x is varying like this, then what will be the shape factor? So we will see this actually when we do numerical. Now one more thing we have to derive actually shape factor algebra and salient features. for shape factor. So you see that shape factor is purely a function of geometric parameter. When two bodies are exchanging radiate energy with each other, the shape factor relation is given by this equation A1, F12, A2, F21. We have already seen that is known as reciprocity relation, right? When all the radiation emanating from convex surface is intercepted by enclosing surface 2, the shape factor of the convex surface with respect to enclosure F12 is unity because convex surface, the radiation emanating from the convex surface is completely absorbed by the body which is enclosing it, right? This is in conformity to the reciprocity discipline. The shape factor F21 is merely the ratio of the area. That is when surface A1 convex, say sphere. F12 is the shape factor, right? Shape factor should be either 1 or less than 1, right? As you can see, it maximum can go to 1. But if it is within, if the area is confined, this convex surface area is confined within the surface 2, so whatever surface that mean the surface 2 can completely see the surface 1. So that means F12, that is the shape factor of 1 upon 2 will be 1. So that's why F12 becomes 1, and then is relationship become A1 equal to A2 by F21 or A1 by A2 F21, right? F21 can be written by just simply the area. And also you remember that F21 and F22, that is the shape factor of 2 on 1 and 2 on upon 2 is equal to 1. And in this case, the black body radiation exchange is given by this formula. Now a concave surface has a shape factor which itself becomes the radiation energy coming out from one part of the surface is intercepted by the other part of the same surface. The shape factor of surface with respect to itself is F11. The concave surface, which is talking about as a concave surface, which has a shape factor with itself, because the radiant energy coming out from one part of the surface is intercepted by another part of the surface. So that's why the shape factor of the surface with respect to itself is F11, because the concave surface, each part cannot see other part. So actually there is a shape factor of one part to the other part, and it is given by F11. For a flat or convex surface, however, the slab factor with respect to itself is 0, because convex surface cannot see its own area or own surface, right? That's why F11 0. This is due to the fact that for any part of the flat or convex, one cannot see or view the other part of the same surface. Just draw this and try to understand, and it is very easy. Now, relationship between shape factor, which is actually one surface we have demarcated into two area. Let's say A1 demarcated A3 and A4, and the receiving area is A2 because light coming from radiation coming from here to here, and then here actually radiation coming from A1 to A2, and A2 is been demarcated into A3 and A4. So we'll see what does the happen for each case 12.5 A and B. If two surface A1 and A2 are parallel and large, radiation occur across the gap between them, so that A1 is A2 and all the radiation emitted by one fall on the other, then F12 equal to F21. That is true. But if one of the two surface is divided into sub area, like this one, right? So AI Fij will be AI Fij. Let us see 12.5A. So radiation from surface A1 has been split into area A3 and A4. So actually A1 F12, so this the original A1 F12 which is falling on 2 can be divided into A3, that is here, and the light coming from F3 to F2, that is F322, and then A4 F42. But remember that F12 is not equal to F32 and F42. It's not the summation, okay? That is the shape factor of 1 and 2 is not equal to shape factor of 3 upon 2 and plus 4 upon 2. That thus, if the radiation surface is subdivided, the shape factor for the surface with respect to the receiving surface is not equal to the sum of the individual shape factor. But however, for the case in the second case, now the receiving surface, initially this is for the originating surface, was split into two area. Now here receiving surface has been split into two area. Receiving surface A2 has been divided into A3 and A4. So now what will be that A1 F12 will be A1 F13. Now original surface remains same, only the view factor is going to change. The A1 F13 plus A1 F14. But for this case, F12 will be F13 plus F14. Okay, because the original surface remain constant. So obviously the shape factor from a radiating surface to a subdividing receiving surface is simply the sum of individual shape factor. So actually we can write this principle of conservation, and actually it you can see uh, let us take the case of an enclosure in which one surface is exchanging radiation with all other surface in the enclosure, including itself. And if it happens to be a concave surface, a concave surface can see view another part of it. The shape factor of a convex surface, which which its enclosure is always unity because all the heat radiated from a convex surface is intercepted by the enclosure. If the enclosure comprises n surface, then the energy radiated from one surface is always intercepted by the other n minus one surface. True, and the surface itself is a concave one. So, five principle of conservation. What actually is saying that if you have n number of enclosure, then from the first surface, the view factor or the shape factor, which are intercepted by the other surface, and the summation of all these individual shape factor is going to be 1. That's what is more important. That is I1 to n f1 minus I, that is originating from the radiating surface 1, will be equal to 1. Similarly, f21, that is that radiating from the second surface, will be 1. Then n surface, all the, so in general you can write j1 to n fi minus j equal to 1 for I1 2 3 n. That is quite easy to understand. Uh, Let us, I think this numericals I have deliberately given black body inside a black enclosure. You have given a black body enclose a black enclosure. Then a tube with a cross section of an equilateral triangle. A tube with a cross section of equilateral triangle. Hemispherical surface and a plane surface. So first case, let us see F21 equal to 1 because all the radiation emanating from the black surface is intercepted by the enclosing surface 1. Now by summation, radiation actually from 1 to 1 and then 1 to 2. That is from radiation from radiating surface 1 to 2 and 1 to 1 will be 1 by summation rule for radiation from surface 1. But by reciprocity theorem, we know A1, F12, A2, F21. So F12 will be A2 by A1, F21. And F11 will be 1 minus F12. This is from this equation. And then F12 is already been given by this formula. You can write this. But F21 already have seen because whatever radiation coming from this surface will completely intercepted by 1. So F21 is 1. So finally F11 become 1 minus A2 by 1. So if you know A2 by A1, you can calculate. So it was also to calculate F11, right? So you see this is the formula for this body. Okay. Now for this body, let us see. Here actually the radiation from this radiating surface is this. So that will be F11, F12, F13. Altogether 1 by summation rule. Already have seen because this is the summation rule, right? And then F110 because the flat surface cannot see itself. So whatever radiation coming from this surface cannot be seen by itself. So F110. So finally you get F12, F13, 1. So F12 will be F13 equal to 0.5 because it is symmetrical, right? This is a triangle symmetrical, right? So F12, F13 will be 0.5. Now for similarly for radiation from surface 2, we have considered surface 1, this surface. Surface 2 will be by summation rule F21, F22, F331. But F22 again 0 by because it cannot see. So F21, F23, 1. So F23 will be 1 minus F21. Now by reciprocity theorem, we have seen A1, F12, A2, F21. This is already you know, right? So F21 will be A1 by A2 by F12. Now A1, A2 same because it's a triangle, semi equilateral triangle. So F21 equal F12. So F23 will be 1 minus F12. F12 you have already calculated 0.5, so it will be 0.5. So all this F12, F23, F321, 31 will be 0.5. Finally, the hemispherical surface and the plane surface. By summation rule, you can write F11, F12, F11, F121. Now reciprocity theorem A1, F12, A2, F21. So F12 you can write A2 by 1, F21. So but F21 is 1 because all the radiation emanating from the surface 2 is been are intercepted by the enclosing surface 1. So F21 become 1. So F1 to become A2 by A1. That is pi r square by 2 pi r square 0.5. Uh, let us look into this example. A 70 millimeter thick metal plate with a circular hole of 35 millimeter diameter along the thickness is maintained at a uniform temperature of 250 C. Find the rate of energy of surrounding at 20C, assuming that the heads of the hole to be as parallel disk and the metallic surface and the surrounding have a black body characteristic. So this is the drawing has been given here. It's a plate and you have a 31 opening. Radius of that opening is given by 17.5 millimeter or 0.0175 meter. Length of that tube is given 70 millimeter, that is 0.07 meter. Temperature is given at 523 Kelvin. The surrounding temperature is given 20 C, that is 300 Kelvin. Now this is a thick metal plate. So we have to go back to the figure 12.10. Let us uh, fix one, designate the cavity, and the surface 2 and 3 denotes the two ends of the 30 millimeter dia hole, which is behaves as a disc. So L2 by R is given by 4 and R3 by L given by 0.0525. And then figure 2.3, you can go back and see F23 is given by the formula 0.065. Now F21, F22, F23 by summation rule all will be 1. But F22 cannot see by itself 0. So F21 will be 1 minus F23. So we have determined already the F23 from this using this expression is equal to 0.06 F13 will be F12 because A1 and 3 are symmetric, right? It will be same 0.1 and 6. So the total loss of energy will be either the formula A1 F12 sigma T14 minus T2 per surrounding 4 and A1 F13 sigma T1 minus T3 per 4. Because here and here both the sides there will be loss of energy. So you just put this value and calculate and you get 6.8 watt. This is another example in this figure 12.1. The area A1 and A2 are perpendicular but do not share the common edge. Find the shape factor F12. So you have to calculate the shape factor A12. That is radiating surface here. It's been hatched area like A1 to this surface F12. In such cases, the shape factor is evaluated by introducing hypothetical surface area because this is not connected A1 and A2. So we have created a hypothetical area A3 and A4 so that the arrangement of perpendicular surface has a common edge. This is the common edge. Now A5 will be A1 and A3. A5, this will be A1 and A3, and A6 will be A2 plus A4. Further, A5, 5, 6, that is this A5 to 6, that is the amount. This is radiating surface, and this is surrounding receiving surface. So A5 to F56 can be divided into A1, F16, and A3, F36. Again, A1, F16 can be again divided into A1, F14, and A1, F12, and A356. So you can write this actually A1 uh, F14 uh, A1 F14 can be written A1 F14 A1 F14 written A5 A54, yeah, A5 A54 minus A334. That is the amount of energy radiating A1 to A4, actually the whole area minus this area. So A5 A54 minus A334. So actually A1 F12 which we need to calculate will be rearranging this term this time. Now in order to get each of these configuration factor, we know F for A56 Z by X, A56 Z by X 2 by sorry 4 by 2. This is Z, this is X, right? This is Z, this is X, and Y by X, this is Y, this is X, this is 4 by 2. So you can use this expression figure 12.4 and then calculate shape factor for each surface. So you can then if you calculated all this, then you put this value A1 you already know 2 by 2, and then F12, and then all the value you put here and then calculate F1 to 0.05 using this the picture I have given previous slides. Now another straightforward example: a filament of a 75 milliwatt light bulb may be considered as a black body radiation into a radiating into a black surface enclosed at 70 C. The filament diameter is given 0.10 millimeter and length is 5 centimeter. Considering the radiation, determine the filament temperature. So all the parameters given. This is the formula, that is the Stephen Boltzmann law. Q equal to psi sigma epsilon A T14 minus to the power 4. Epsilon coming because it's a not a completely black body, so emissivity is not one, right? But we are considering it's a black body radiation, so again emissivity should be one. But again, you have write this expression. This is the standard expression for any body, any real body. If it is a black body, emissivity becomes 1. Now for the area, for that you can calculate pi dl, that is that d is the diameter, l is the length, and then you put this value, and then T1 and T1 given, T2 you have to calculate. Sorry, T4, T2 is given, T1 you have to calculate filament temperature. So you have to calculate the filament temperature is, and then you see it is 2756 C. Let's use the Stephens-Boltzmann's law. Another problem: two parallel rectangular surface, 1 millimeter and 1 meter by 1 meter by 2 meters are opposite to each other at a distance of 4 meters. The surface of the are blacks and at 100 C and 200 C. Calculate the heat exchange by radiation between these two surfaces. The heat flow between these two surfaces is given by 1 Q12 A1 F12 sigma T14 minus 2 to the power 4. We are considering black body radiation epsilon 1 epsilon 2 1. Now from this figure, x by L, this is this by L, that is 2 by 4 0.5, and y by L, this by 4 1 0.25. So F12 again from this figure 12.2 you have to see, and then it is 0.043. So F12 0.043, then Q12 will be A1, that is 2 into 1 area 0.043 into Stephen-Boltzmann's constant 5.67. Then T1 given already 273, uh, sorry, 200C, that is 200 plus 273 divided by 100 to the power 4 minus 100 plus 273 divided by 100 to the power 4. We calculate 149.5 watt.